not just scripted for the video driver and the recorder?
I tried to look into how to do it. I could not find out, how to use a script to do exactly the same thing that I did interactively. I'm pretty sure there's a way to do it. I just could not find out, exactly how to do it yet.
Well, it looks like right now you have like 2 configurations and you're just copying over the default, right?
You mean with the video driver?
Yeah.
The video driver, I have to run the configuration program, which should be run automatically too, just to find out what driver is appropriate. But for some reason, it does not work well, in this case. So, I'm looking forward to an update of the operating system, so that issue will no longer be a problem. Let me go ahead and turn off some of these lights. Better contrast. And let's get started. Are there any questions about the homework assignment for this class, which is the return values homework assignment? It's a little tricky, okay? But did you get it done? Or do you know how to proceed?
Well, I got it done. I don't know if it's ready.
Okay.
I don't know if we're ready yet, so
All right. How about the examples that we have gone through last week? Are there any questions about those examples that we went through in the class? Yep.
Have you uploaded them to Moodle?
I guess not. Well, let's go ahead and do it first. Let's go to the home folder. Last week will be the 24th, so this will be the right folder. Because if there are no questions, we will move on to records and user-defined types today. If there are any other questions related to subroutines, we can go through some of those topics. Yep.
Let me see if I've got the name of this file here. It was the trace of subroutine find minidex.
Find min index.
Minidex.
Yep. Minimum index. The index of the minimum element.
Yeah. I had a problem with that on it was the 12th line of the trace.
Okay, let me upload this first, so that I don't forget to do it later on. This will just take a
I'll just look at it online. Actually, that's probably better use of time.
Well, I'm almost done with that. And we have the file from last Thursday now, and which has the find min index program. So you don't want me to go over that again, or is that what you guys want to do?
I just had one question on line 12.
Okay, let's go ahead and do that.
Because we
Hold
said
on a
that,
second.
let's see, that b is less than bar a bar minus 1 is true. And it
Okay.
was false.
Well, I'm just waiting for the screen to pop up, or I can just go here and look into that. Okay, which subroutine would that be? Would it be find min index? It has its own file, right? Okay. And your question is about line 12 in the pseudocode or line 12 in
Line
the
12
trace?
in the trace.
In the trace? Okay, let's go ahead and take a look at the trace now. Okay, this is the trace, that's the code, and your question is on row 12. Is that right?
Yeah, why
Okay.
is it just b is less than bar a bar instead of bar a bar minus 1?
Because on line 7 of the pseudocode, we do compare to just bar a bar.
Okay.
That's why.
Okay, I just got a copy of
Okay. Any other questions about the find min index sample program?
Bar a bar is 4.
Bar a bar in this case is 5 because bar a bar is the number of elements in an array, not the index of the last element in the array. Okay. Any other questions about this one? This is basically the precursor to the selection sort algorithm, which we also traced at the end of the class on Thursday. So are we still doing okay so far with subroutines? How about the concept of return values? Is that okay? Does everybody understand or feel comfortable with the concept of returning values? It's all good? All right. If everything is good, then we'll go ahead and move on to the new topic. I already turned the highlight on in topic 9. And this is a new topic. It talks about records and user-defined types and also other types of nested aggregate types, which basically means we can group items other than using arrays. Arrays is one way to group items together, but a record would do something different. It has a different purpose compared to arrays. Let's go ahead and take a look at this slide here and show only this frame. And here's a rationale of using, why do we want to have records? Now you should have read some of this stuff already, because you should be reading ahead of me just a little bit, so that you know what topic I'll be covering on today, on a particular day. Records are really just the same as a form in real life. Okay, what was the last time you actually have to fill in a paper form? Must be a while back, because we don't really use paper forms these days anymore. But let's just say that you want to go to our admission and records office and try to register, go through the whole registration process, but using paper forms. Now, what do you see on a form? I can, I have a dry marker here, so I can actually draw the form here. So what do you expect in a registration form to get started with taking classes at ARC? It'll be names, okay? So you will have, a field for first name, last name, date of birth, okay. What else? Address, okay. So with address, you have multiple lines because you have your address, you have your city, state, zip code, and so on, okay? And all of these items are on the same sheet of paper. Is that right? Okay. Now, what if I tell you that instead of doing it like this, I'll give you little pieces of paper. One piece of paper just for your first name. One piece of paper just for your last name. One piece of paper just for the month of your date of birth. One piece of paper just for the year of your date of birth, and so on. So you end up with a little pile of tiny little pieces of paper. Now, how would this, which is one single form, the normal way of doing things, compared to a pile of little slips of paper, each one only containing a very small amount of information? How would those two approaches compare?
The little pieces of paper can be reorganized in different ways. Like you could sort it for just months or just...
Okay. And what if you have your form already filled in and you run into somebody else who also has his or her form already filled in, and then you just kind of spill all the little slips of paper all over the place? Now, it's not a problem with you or the other person because you recognize your own name, you recognize your own address, you recognize your own zip code, your phone number, and so on. So it's not a problem. What if you turn in the form already to the people behind the front desk at admission and records, and those people make a mistake, they run into each other, and then you have these piles of little slips of paper all mixed up. They don't know which one is whose. So now we have a problem. And it's the same thing in programming. Okay, so we'll go ahead and take a look at this sample program here. How many people already know what a complex number is? Okay, very few, but that's okay. We can just use this as an example. Okay. What a complex number is it has a real part and also an imaginary part. Okay, so there are two parts to a complex number. In order to compute the sum of two complex numbers, you have to add up the real number part to become the real number part of the sum, and then you have to add up the imaginary part to become the imaginary part of the sum. So that means in order to provide or to supply two complex numbers as parameters, we'll need four individual numbers because we need the real part of the first number, we need the imaginary part of the first number, we'll need the real part of the second number, we'll need the imaginary part of the second number, And in order to pass the result back out, we also need two parts, because the sum has its own real part and the sum has its own imaginary part. So it will require 6 individual parameters just to add 2 complex numbers. Well, we can do it. Okay, this is how we use the 6 parts. The real number, the real component of A and B will be added and become the real part of the sum. The imaginary parts of A and B will also be added to become the imaginary part of the sum. But we have a little bit of a problem here, because in order to use this, we need a program to look like this. Okay, we need 6 individual variables, and when you invoke the subroutine, it will look like this. Now, it's okay, but it's easy for me to make a mistake. In other words, in this case, I did not make a mistake. I used the R of X to pass to the R of A. I used the I of X to pass to the I of A, and so on and so forth. But it's easy for me to make a mistake here so that the calculation is not going to be what we expect it to be. Because every time you have 6 parameters to pass, and each one has exactly the same type and the same look as the next one, it's very easy to make mistakes. And we want to minimize our chances of making mistakes. So this is not the best way of doing things. It is equivalent of having your forms basically cut into little slips of paper, and it's easy to lose track of the little slips of paper or get confused. You have 2 students' applications, and it's easy to confuse and pick up the wrong piece from the wrong application. What we want to do is to be able to define our own types. So before we do that, let's go ahead and talk about types in general so that we know what types are, and then we'll go back to this and say, how can we make a type for complex numbers so that we can handle a complex number as a single item when we need to. Now you can read this slide here, it's just kind of, this part is a little bit confusing because it does not render somehow the symbol is not translated correctly. So what I'll do is I'm going to use a text editor to give you some examples, and you guys tell me what you think about it. What is that? 3 plus 4. First of all, does it make sense? Does it make sense that I can perform that calculation? It's okay. I mean, 3 plus 4 is 7. Okay, ask any elementary school student, and they can give you the right answer. Let's say true or false. Can we find out the result of the disjunction, true or false? Yeah, I mean, it makes sense. I mean, disjunction requires a Boolean on either side. True is a Boolean value, false is a Boolean value, and the result turns out to be true by the definition of disjunction. So that's good too. We don't have a problem with that. Let's try something that seems to be a little bit more tricky. 43 is less than 23. Can we evaluate whether this statement is true or not? This condition, whether it's true or not? It turns out to be false. Okay, but there's no problem of evaluating the condition and come to the conclusion that it is false. Okay, 45 is less than 23 is not true. Okay, so now let's look at something that is just doesn't seem to make any sense. Let's look at 3 or 4. Okay, what is the result of 3 or 4? It should be undefined. Okay, it doesn't make any sense. Okay, it does not make any sense because the disjunction operator requires a Boolean on both sides. And in this case, we have a numerical value on one side, and we have another numerical value on the other side. So technically speaking, this does not make any sense. I can give you some other stuff that does not make any sense. Okay, what is true times false? That's multiplication. Okay. Well, once again, it does not make any sense because multiplication requires a number on both sides. In this case, we have a Boolean on one side and we have another Boolean on the other side. So it just does not make any sense. Let's try something else. Okay, let's try, true is less than 72. Once again, it does not make sense because when you use a less than symbol, you have to have numbers on both sides. You cannot just have a Boolean on one side and a number on the other side. What I'm telling you right now is the first three examples that we have here, these three, they make sense because the operators are getting the right kind of value to work on. So they make sense, we know how to carry out those calculations or operations. The other three examples do not make sense because the numbers or the values that we supply on both sides of the operator do not match the type that we are expecting, the kind of value that we are expecting. Are we doing okay so far with these 6 examples? Why the first 3 cases are okay, and then the second 3 cases are kind of iffy. We don't quite know what to do with them. Is that okay so far? So that's your first exposure to a type, because essentially a type is dictating what kind of value we are expecting for certain operators. Okay? So in the case of addition, what do you think are the types of the two sides of the addition operator?
Numbers.
They have to be numbers, something that can be added. With disjunction, what are we expecting on the two sides? They have to be true-false values. They have to be Booleans. Okay? Okay, very good. And I can give you a whole ton of other examples. For instance, I can give you something like this. 23 with an index operator and give it a 6. That does not make any sense because 23 is not an array. The index operator, the square bracket operator, only makes sense when you are using it on an array. When 23 is not an array, it does not make any sense at all to use the index operator. Okay? So are we doing okay so far with what operators expect in order to perform operations? Is that okay? All right. So we are going to switch back to the slide here, which is going through the same thing, and then we have 3 different types of built-in types with almost every single programming language. The first one is integer. Integers include positive whole numbers, negative whole numbers, and also 0 itself. So that means negative 25, 299, 0, and so on and so forth. They're all integers. 4.2 is not an integer because it is not a whole number. Pi is not an integer because it is not a whole number either. It is not even rational. It's an irrational number. With integers, we can perform the usual operations, which is multiply, divide, add, subtract, and so on and so forth. We can also compare using less than or equal to, and all the other comparison operators. Now, why do you think we focus so much on integers like these, while real numbers are not as they do not get as much attention in programming? I know in mathematics we work with real numbers all day long, but in programming, how come integers are more important in general? No question? No idea? Okay.
Easier to represent in binary?
Sorry?
They're easier to represent in binary?
Very good. They are easier to represent as a base 2 number. Okay. Have we talked about base conversion in this class? No? I had a program. Did I explain the approach to do it? Like by hand? No? Okay, let me just explain, base 2 conversion, which is something that we can all do fairly quickly. So here's an example, okay? Because I want to explain, why in this entire class I don't really put much attention to real numbers, okay? 6.25, or the number of pi, the value of pi. Why don't we use, real numbers for the most part? Okay, let's take a look at a number, let's say 67 in base 10. So without a suffix, I can only say 67 in parentheses 10 to represent this as a 67 in base 10. Okay, how can I represent this using a base 2 number? But that's too hard. Tack, you never really talked about base conversion. Well, that's true. I never talked about base conversion, but base conversion is easy. How many of you think that you can work in McDonald's or a fast food place and be able to look at the change, the value of change, and come up with the correct number of bills and coins with the least number of bills and coins? How many of you think that you can get that job done? Okay, not quickly, just know how to do it. Okay, and I can tell you that's harder than base conversion already. Okay, you're just coming up with the correct number of bills and coins, in order to work at McDonald's, Carl's Jr., or Safeway. Well, Safeway is not one of those things because they have the automatic thing, so it's cheating. By coming up with the number of coins and whatnot is actually harder than base 2 conversion. Let me explain why. So this is kind of like a digression, and we do have time for a digression, and I think it is extremely important for anyone who wants to get into programming to understand base 2 versus base 10 representation. Okay, so let's take a look at the kind of values that we can represent using U.S. currency systems or coins and bills. What is the smallest one? First, the smallest one is a penny. It's a cent, right? So let's just use everything based on a cent. Okay, so this way we don't have to do conversion using the 0.01 as a unit. So 1 cent is the base unit. What is the next one up? Okay, let's just look at the more common ones. Okay, so half dollars would not be on this list. And the next one up is what? 10, and then 25, 100. Okay, I know we have half dollars, but they're not common. So we have $1 bills. We do have $2 bills, but once again, they're not common. So the next one up is a $5 bill, $10 bills, $20 bills, $50 bills, $100 bills, and so on. Do you see any regularity here? I don't. Okay, from 1 cent to a nickel, it's a multiplier of 5. From 5 to 10, it's 2. From 10 to 25 is 2.5. From 25 to 10 to 100 is 4. So far we have not used the same multiplier, yet. And then from $1 to $5, it is the same. From $5 to $10, it's the same. And then we don't go to $25, we go to $20 instead. So there's no regularity, and yet you can handle it. Okay? What about base 2? If you want to work with base 2, you just have to imagine that all the units of all the bills and coins that we have, they are all powers of 2. In other words, we have $1 bills, okay? We have $2 bills, we have $4 bills, we have $8 bills, $16 bills, $32 bills, $64 bills, and so on. Okay? That's it. Okay? If you know how to make change, using the correct number of bills and coins using our existing currency system, you already know how to do with base 2. In other words, if I want to express 67 strictly using a combination of powers of 2 and using the least number of powers of 2, how would I express 67? Well, let's take the biggest chunk out first. What is
60.
the large?
60.
64. Okay, the largest number that is a power of 2 that is less than or equal to 67 is 64. Well, 64 will give us a remaining portion of 3. So with 3, what is the largest power of 2 that is less than or equal to 3? 2. That's 2, with 1 remaining. And 1 is already a power of 2. It is 2 to the power of 0. So this way we can rewrite it. What is 64? It's 2 to the power of what? 6. Okay, and what is 2? 2 is 2 to the power of 1. And 1 is 2 to the power of 0. Very good. All right. How do you think we'll represent 2 to the power of 6 as a base 2 number? 2, it will be 1 followed by 6 zeros. It is quote unquote a million, but in base 2. Well, let's take a step back here, okay? Because we want to understand why that is the case. Let's take a look at an arbitrary base 10 number. Okay, let's pick that one. What is this base 10 number? 7,281, right? What does that mean exactly? Well, let's break it up. It's 7,000 plus 200 plus 80 plus 1. It's kind of obvious, right? Okay, we should not have a problem with this step here. But what is 7,000? 7,000 is 7 times 1,000, plus 2 times 200 is 2 times 100, and 80 is 8 times 10, and 1 is 1 times 1. I mean, tech, come on, this is college. It's not elementary school. But where am I heading with this? Okay, we want to convert everything now to powers of 10. So what is 1,000 as a power of 10? 3. And 100 is 10 to the power of 2. 10 itself is 10 to the power of 1. And 1 is 10 to the power of 0. Do you see a pattern here? In other words, every single digit of a base 10 number represents how many of a power of 10 do we have. So can we convert and use the same concept over here? 10 to the power of 6 as a base 10 number is what? It's a million. How do you write a million as a base 10 number? 1 followed by 6 zeros. The number of zeros is the power, to the base that you're using. We're using base 2 here, and the power is 6. The multiplier is 1. So this means we have 1 times 2 to the power of 6 plus 0 times 2 to the power of 5 plus 0 times 2 to the power of 4, and so on. It's going to get fairly boring. And then we get down to 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. Now, if you just compare this representation here and this representation here, do you see any common pattern to it? Okay, we have powers of a certain base. In the first case, we have a base of 10, so the powers are all based on 10 to the power of something. And here we are using base 2, so we have 2 to the power of something. We also have a multiplier to specify how many of those powers of 10 do we need. And here we have a multiplier of how many of the powers of 2 do we need. Do you see the common thread here? So now, when you want to represent 1 times 2 to the power of 6, 1 times 2 to the power of 6, it is 1 followed by 6 zeros as a base 2 number. Okay, the zeros we don't really have to deal with, because they're all zeros anyway. But then you have 1 0 to the power of 2 to represent this number because it is 2 to the power of 1. This 1 gives us this 1 0 here. In other words, the power to the base specifies how many zeros do we need in order to represent that number, that value. And then the last one is just a 1 in base 2. 1 is 1 regardless of the base. So now if you add up these numbers, can someone kind of guess what it looks like in base 2 when you add up all these numbers?
1, 4 zeros.
1, 1 in base 2. Okay? It basically means we have 1 of 1, 1 of 2, 0 of 4, 0 of 8, 0 of 16, 0 of 32, and 1 of 64. I think that's easy. That's easier than base 10. It's just that we never really look at things that way because we are so used to base 10, and our currency system, just like what I have demonstrated here, is really awkward compared to base 2 or any type of base number because there's no regularity to the multiplier to the next level of coins or bills. So are we doing okay so far? So do you think any integer can easily be converted into base 2 representation? It's the same approach. I mean, it works with, negative numbers is a little bit tricky, so I won't talk about negative numbers in this class, but with positive integers, including 0, it's pretty easy. How would you represent fractional values in base 2? Well, first of all, do we actually get to deal with fractional numbers in base 2 in real life? How many of you fix cars occasionally? Okay, and how many of you have wood projects? Okay, woodwork projects occasionally. Some of you do. Okay, how do we measure the drill size or socket size in SAE? they're all fractional of inches, right? Fractions of inches. And what is the base of those, fractions? Are they arbitrary? Do we have, like 5/17 of an inch? No, we have 5/16, right? They're all powers of 2, exactly. Okay, so that's how we represent, measuring units when we are talking about sockets and also drill sizes when you talk about SAU unit instead of metric. Okay, well, let's take a look at those numbers. So we are now talking about fractional numbers here. So let's say, which drill size do you want to talk about? Because I can do the conversion anyway.
5/8.
5/8. 5/8 is easy. Okay, so let's take a look at 5/8 here. Okay, 5 divided by 8 is a base 10 number. Can I break it up into fractions that is 1 over a power of 2? Just combinations of those. Well, sure we can. It is 1/2 in base 10 plus what? 1/8 in base 10. Right? Because 2 is a power of 2, and so is 8, which is also a power of 2. How do you think we'll represent? Oh, well, let's do this. This is the same as 1 times 2 to the power of what? 1, negative 1. Okay? And this one is 1 times 2 to the power of what? Negative 3. All right, very good. So let's kind of stop here, and then we'll take a look at a decimal number. Okay, as a decimal number, we have. Okay, let's just look at this number here as a base 10 number. Now this base 10 number obviously is just 0.2 plus 0.03 plus 0.007. But what exactly is 0.2? 0.2 is 2 times 10 to the power of negative 1. 0.03 is 3 times 10 to the power of negative 2. And 0.007 is 7 times 10 to the power of negative 3. Do you see a pattern here? So that means when we have to convert these into binary decimal numbers, this one becomes 0.1 in base 2, and this one becomes 0.01 in base 2. And when you add up these two, it becomes 0.11. Oops, I take it back. I made a mistake here. That will be 0.001, because the 1 is 3 places after the decimal point, or binary point in this case. So when you add up these two numbers, it becomes 0.101 in base 2. 0.101 in base 2 represents exactly the same value as 5/8 in base 10. So we have been using binary numbers even in terms of fractions before we know that they are actually base 2 numbers. Okay? Or this is just another way to look at it. Now, how do we represent, say, 0.2 in base 2? It turns out to be a recurring number. It cannot be represented using a fixed number of digits. It's just like 1/3 in base 10 is 0.3333, and it never ends. And it's the same thing. 0.2, which is 1/5, cannot be represented exactly using a fixed number of digits. So that means fractional numbers are much more tricky to deal with, and that's why we kind of focus on just integers, because we can always represent integers using a fixed number of digits. And that's why this is a digression to show you guys why we kind of focus on integers when we talk about programming. We can represent fractional numbers, but it is not quite what you expect, because all we can do is to represent certain points with a fractional, with a real number line, and between those points, those numbers cannot be represented. Okay, so this is not the right class to talk about floating point representation. We'll just kind of focus on integers, in this class. The next type of values that we have dealt with so far are Booleans. Okay, Booleans, a Boolean value can either be true or false. They work with conjunctions, disjunctions, negations, and the result of comparisons are also Booleans. It's either true or false that x is less than y, or something like that. This one we have not really used in this class, but in programming it is extremely useful, A string is basically some kind of text value. You can use a string to represent a name, an address, a city name, and so on and so forth. Those are what strings are good for. We don't really use strings too much in this class either. Okay. So do we have any questions at this point? Yep.
You said earlier that an integer couldn't be used as the name of an array, but could it be used as a string for the name of an array?
Can it be used as the...
Like for earlier you gave the example of 23 with the element with the index of 6, and you said it wasn't valid because it was an integer. But if you use 23 as a string, would that be a valid array? Like, could a string be used for an array?
You mean in C? I think
meant
you
in
might
general.
be able to do that, although it's not usually done that way. But I suspect that the types would work out. But that's kind of tricky. If you use a literal string to do it, that's kind of tricky.
So it wouldn't generally be... So there isn't like a practice of using strings for arrays?
That's a representation issue. It's not necessarily that a string is represented as an array. It's not always the case, even though it makes sense. So here, what this particular section talks about is, how do we integrate the concept of types into, what we have talked about so far. So what we'll do is, we'll just say before, we'll just say, by value, we'll just say local something, and now we'll also append a little bit of more information and say that n is not just a by value parameter, it is a by value parameter of the type integer. We'll also indicate the local variable f is not just a local variable, it is a variable of the type integer. It can only be used to store integer values or integral values. You can also do the same thing with return. Basically, you can say return type is an integer, which means the subroutine find factor can only return a value that is of the integer type. In other words, we are just extending what we have already discussed in this class by including the specification of types when we talk about parameters, local variables, and also the return values of a subroutine. Are there any questions about this part here? We're just adding a little bit more to what we already know that we have already done, but so far there's no impact whatsoever to algorithms in general. Any questions? No questions? Okay. If there are no questions, this is binary search, as an iterative, subroutine. So instead of just saying by value or by reference A, we'll say that this is an array of integers. Instead of just saying by value K, which is the value we're searching for, we have to say that K is an integer. Instead of just saying the return something later on, we have to say what we are returning, and the return type is a Boolean, and so on and so forth. So this is just a change to what we do. Line 20 is an artifact; it should not be here. So that's why it's just think that line 20 does not exist. It's a typo. Okay. Now let's go ahead and talk about records. In other words, let's go back to how do we define our own type. I should have used an example that is more easy to understand without knowing what complex numbers are. What about dates? How do you represent a date? Year, month, and day. Okay. Is that really a good representation? It's good for people, but how do you compute the number of days between two particular dates?
It's arbitrary because months have different...
You can do the calculations, but it's not straightforward. Okay. In other words, if I want to find out how many days have elapsed since, let's pick a random date here, since 1996, April 3rd to today, can someone come up with the answer quickly? No. Because our calendar system does not really lend itself to computing the number of days between two particular dates. Okay, but nonetheless, we use that to represent dates. let's go ahead and write a sample program utilizing records, and this will serve both as an example of what a user-defined type is and also how it is represented. So we'll go ahead and take a look at this. Okay. Any type of user-defined type in this class will start with the name record or keyword record, and then you have to supply the name of the type itself. Since we are talking about how to represent a particular date, we'll just say that it is a date. It is only a convention that the name of a user-defined type to start with an uppercase letter. It is only a convention that is observed by all programming languages. But if you want to, you can actually use a lowercase. It's not a problem. But other programmers will frown at it because it is a convention to always use an uppercase to represent the name of a user-defined type. And once again, what do we have in a date again? We have a year component. Okay. How do you represent a year? What kind of type should I use to represent year? Integer. Very good. So we'll say year is an integer. What else do we need to represent in a date? A month. Okay. So I can use a string to represent a month, but that's not very handy. What would be a little bit easier to deal with to represent a month? Another integer. Very good. Okay. And then we have day of month, which is also going to be an integer. And this is how we represent a particular date and record. Okay. What I have defined here is a new type. In other words, this is date starting with an uppercase D can now be used as integer, as boolean, as string. I can use it to manufacture more of the date objects later on. Okay, let's go ahead and just make it one example. I'll define a subroutine and I'll just call this stub. Okay, which means it really doesn't do anything except I can define local variables inside this subroutine and use the local variables on some other with other subroutines. Okay. Stub is going to define a local variable, and I'll just say, let's see, first day of class. Okay, so first day of class. Okay, we'll just call it first day. And now, since we have already talked about the concept of types, every time I define a local variable, I will have to supply the name of the local variable. But at the same time, I also have to specify the type of the local variable. In this case, first day is a date. So this is what I will do. Okay. And let's just make this example easier. All we want to do is to initialize first day. Now, this becomes a problem because when you initialize first day as a variable, you cannot just use one single assignment operation because it has how many components? It has 3 components. And each assignment statement can only deal with one integer value at a time. So this won't work. I cannot just use first day gets a value of something, not in the pseudocode that we talk about in this class, and also not in C. In some other programming languages, you can actually do something like that, but not in this class. So that means I have to specify which component do I want to initialize first. It doesn't matter what the order is, I just have to be consistent. First day.year is, let's say it is this year, it's 2011. First day.month is, let's just say, January, and we'll use 1 to represent January just to be more intuitive. And then first day.don, or day of month, is going to be, what is the first day of class, for this semester? Is it the 18th? We'll just put the 18th here. And this is how we initialize a local variable, first day, that is of the type date. And we have to initialize the 3 components one by one. One assignment operation can only deal with one component at a time. The dot notation here, let me use the screen. The dot component, when we say first year dot year, this dot is the same as apostrophe S in English. In other words, we are literally saying first day's year. Are we doing okay so far? Now the year component of a date is an integer, and the right-hand side is an integer, so this assignment operation is fine. There's no problem. Are we doing okay so far? Now right here I am illustrating a particular concept that will become useful later on, or it is very important in all your future classes. You have to distinguish what a date is, D-A-T-E starting with an uppercase D, and what a first day is, which is a local variable. Those two things are completely different things, even though they are related. When I define date with an uppercase D, I am making a cookie cutter. Okay, this is a cookie cutter. When I say local variable first day is of the type date, I am using the cookie cutter to cut out a cookie, and that cookie is a local variable. Do we understand the differences between a cookie cutter and a cookie? Which one can I eat? The cookie cutter. Well, I'm not a bender, so I cannot do that. As in Futurama, right? Okay. So I can only eat cookies. I cannot eat a cookie cutter. So with a single cookie cutter called date, how many cookies can I cut out using that particular cookie cutter? As many as I want. Okay? What is the limiting factor of how many cookies I can stamp out of a particular cookie cutter?
How much dough you have.
Exactly. How much dough do I have? So what do you think, cookie dough is equivalent to in the programming world? Memory. Exactly. So in this case, defining the cookie cutter date does not use any cookie dough at all. I can define 5 gazillion cookie cutters, and that won't use up 1 single ounce of cookie dough. But when I stamp out local variables and parameters and global variables using the cookie cutters, I start to use up cookie dough. Okay? This local variable, first day, is a piece of cookie. It has a name of first day, but it's a piece of cookie. It uses up cookie dough. The variable date here, the type date is a cookie cutter. It does not use up any cookie dough. So can we differentiate the purpose of the type as opposed to the concepts that we already know, which are variables and parameters? Is that okay so far? Now that's the terminology that we use up to this point. When you move on to C++ or cisp300, the record type is also called a class. Okay, in other words, instead of using record, your next class in cisp300 will refer to date as a class. It's the same thing. Okay, it's just a different name, but it means exactly the same thing. A class definition is a cookie cutter. When you move on to the next class, first day sometimes will not be called a variable. Sometimes it will be called an object. An object in an object-oriented programming is basically a piece of cookie, and you have to supply the cookie cutter so that you know what is the shape of that cookie that you're cutting. So these terms are basically equivalent. Let me just write it down in the text file, and then make sure I save it too. Okay. In cisp300, in cisp360, and in the kitchen. Okay. So in this class, if I say something is a record, in cisp360, it is either called a struct or a class, depending on the context. But either one will work. They're basically the same thing with minor differences. So they can it can either be called a struct for structure or a class. In the kitchen, this is a cookie cutter. In this class, we use variables. In cisp360, they can use variables, and sometimes they will use the term object. In the kitchen, these are basically cookies. Okay. In this class, we use the term columns. Okay. Every column represents something. In cisp300, I don't think they have any specific name for that, probably just memory. And in the kitchen, we'll call those, cookie dough. Okay. Okay. So this is a small, tiny little table to give you, how in this class, we call something a record. In the next class, it will be called a struct or a class. But in terms of concept, it is equivalent to a cookie cutter. In this class, we call our variables variables. In the next class, they can still be called variables, but sometimes they can be called objects. And objects or variables are basically cookies that you cut out of cookie dough using cookie cutters. And every piece of cookie must be cut out by a particular cookie cutter, because a cookie cutter is your type. And then we have columns in this class. Okay, every single time we invoke a subroutine, we allocate columns. Every time we return from a subroutine, we free up the columns. Columns are basically memory in cisp300 and all other programming classes, which in the kitchen analogy, they're equivalent to cookie dough. Okay, so the more variables you make, then the more memory you're consuming. And if you use recursion, it takes up more memory every time you invoke the same subroutine. So those are the equivalency of terms. Let me make sure that we save this into today's folder, because I think this will be useful. And since we have time in this semester, I think we can get into object-oriented programming just a little bit in this class, which is going to be useful. So here we have examples. Okay, sometimes I use the same examples as in the in-class example, and sometimes I don't. And this time, I use, it's consistent with the same module here. I'm defining, a complex type. Remember, this time, complex starting with uppercase C is the name of a cookie cutter. The cookie cutter defines the shape of the cookies. In this case, the shape of the cookies is that they have two components. The first component is called I, which is a number, and the second component is called R, which is also a number. If you compare that to the program that we have up to this point, this is basically the same thing. Okay, they're basically equivalent stuff. Do we have any questions at this point? No questions?
Well,
yep, go ahead.
Here we're calling it integers,
Mm-hmm.
but in the other example you showed us, the record you said it's numbers.
Yes. It's just a general type that I call number. That can be real numbers.
Okay, so
Yeah.
it doesn't actually change what it can go into. It's just
It does change, because I in this case you can store any number in I,
Right.
including irrational numbers. But in reality, when you write programs, you cannot store irrational numbers. You can only store approximation of irrational numbers. In fact, many rational numbers cannot be represented exactly either. Like 22 divided by 7, cannot be represented exactly.
Right.
It's just we can only store an approximation of that value. So are we doing okay so far with this? Okay. Let's make this program a little bit longer. Okay. So we'll go ahead and insert and define another local variable, and we'll say last day, and we have date here. And we'll go ahead and initialize last day dot year, same year. Month is May, and DOM, day of month, is it like the 18th, 15th, or something like that? I think it's the
Today?
no, the end of this semester. End of the last class. I'll just use that as an example, doesn't matter. Okay. All right. So now we have the initialization of two particular dates. Does anyone want to find the logic or define the logic to find out the number of days between two particular dates? It's not going to be easy, so I'm not going to waste too much time with, on this. How about comparing, just to see whether a particular date is before another date? That would be easier, right? Just comparing. Okay. So So let me just write, this subroutine here. Print invoke is earlier than, and this time I can pass the entire first day as one thing. So we say first day is going to pass by, in this case, pass by value to a parameter. I have not defined the subroutine yet. I'm going to define it next. Okay, first day will pass to x. I just called it parameter x, and then last day is going to pass to parameter y. And let's just say that that's the end of this subroutine. And what's up? And now I will go ahead and define the subroutine is earlier than, which has two parameters, by val x. But this time I cannot just say by val x because I also have to indicate the type of x. What do you think x should be? An integer, Boolean, string, or date?
Date.
It should be a date because I passed first day, which is a date, to this parameter. The argument that you pass to a parameter must match the type. Now this is also a good time to kind of give you guys an introduction to what is an argument as opposed to what is a parameter. X is a parameter because it is a by val something that is defined in the subroutine. First day in the context of the invocation is called an argument. In other words, you use an argument to specify a parameter. Is that okay so far? Those two terms, sometimes are used interchangeably, but if you look at it strictly, they are different things. Yep.
Can you say that one more time?
Okay. The first day in the context of this invocation is called an argument because this is what you use to specify the parameter x. X is a parameter because it is defined in the subroutine itself. And it is a date. And then we have y, which is also a date. Now, how do I tell someone whether a particular date is earlier than another date? We can use the less than thing. Okay, so if I use a single return, what do I say? Well, first of all, I don't want to look at day of month or even month first. I want to look at the year. Because if the year of the first date of x is already less than the year of y, I'm done. Okay, I don't even need to look at the month or the day of month. So I will say, well, let's see, if x dot year is less than y dot year, then we're good to go. Well, but what if it is not? What if x dot year is greater than or equal to y dot year? Well, then we need to look at something else. Let's not do it this way. This is like the really shorthand version. So we'll do it using the longhand version. So we'll say if x dot year is less than y dot year, then we can just say return true because the first date is in fact less than the second date. Is that okay? The else part, I only have to say if x dot year equals to y dot year. Then I do something because I have another else down here with nothing to say return false. Well, let's just take a look at this logic here and find stuff. I can always insert additional lines later. And we'll fix up the indentation. Okay, does it make sense so far? If the year of the first date is less than the year of the second date, then I can say the first date is earlier than the second date. Is that good? Otherwise, if the year of the first date equals to the year of the second date, I have to look into the month. Right? What does this else correspond to? The year of the first date is greater than the year of the second date, in which case I can definitely return false because the first date cannot be earlier than the second date in that case. Okay, so now we get into this part here, which is basically saying I know already that the year of the first date and the year of the second date are exactly the same. What should I look at next? The month. Okay, and I can use exactly the same logic. I can say if x dot month is less than y dot month, that would be easy, because in that case I can just say return true, because the first date will be earlier than the second date. And now I have to insert some additional rows. Just undid one of the operations here. And I need to make sure that I use the right indentations. Okay. So is that part okay? Then we want to say, well, what if x dot month is not less than y dot month, but they are the same? We'll deal with this later. And then we have another else. Okay, we have to fix the indentation of these two, and then insert some additional rows. Okay, let's deal with the easy one first. This is the easy one. By the time I get here, that means x dot month is not less than y dot month, and x dot month does not equal to y dot month. What is the only possibility left? Return false, because x dot month is greater than y dot month. So I can just return false here. Okay, so right here, at this point, I know the year and the month are the same between the two dates. So I can only rely on the day of month in this case to return the answer. I can use conditional statements, but I can, at this point, I think I can just use a single return statement and just say return x dot dom is less than y dot dom, because that is my answer. Is everybody convinced that this is this is sufficient? Because at this point, how do I get here? I can only get here if x dot month equals to y dot month and x dot year equals to y dot year. They are of the same year and of the same month. Well, if I know that two dates are of the same year and the same month, what do I use to determine which date is earlier than the other one? I only have to compare the day of month. And that's why a single day of month comparison will return the answer for the entire subroutine at that point. Because we have we have only two choices here. Either x dot dom is in fact less than y dot dom, which means the day of month of the first date is less than that of the second date, which means yes, it is true, or they're not, or the first one is not less than the second one, in which case I am supposed to return false. Are we doing okay so far?
So you're saying that if you return that, it will automatically...
It will first perform the comparison, and then whatever the comparison gives me, I will return that as my result. Okay. And just as my notes indicated, you can. I'm also supposed to say the return type is a Boolean, so that whoever is invoking the subroutine will know how to use the return value of the subroutine. Okay, so this is my program. It's rather long, and we'll go ahead and track it down and see what it does. It's long, but it's mostly just tedious work. When you actually trace it, it doesn't really work. It doesn't take that long to trace. Let's go ahead and save it first. Okay. Here. And we also need one extra line outside of the entire thing to invoke a subroutine called stub, because otherwise nothing gets executed because they're all within definitions of subroutines. So now we go ahead and track it down to see what it does. Okay. Using sheet 2, we need comments. This will take up a lot of columns because we have all these dates that are being passed around. First of all, as the precondition, do we have any global variables in this case? Are all the names accounted for as either local variables or parameters of either kind? They're all taken care of. So there's no real precondition to speak of. Then we start execution on line 35, which is to invoke the stub subroutine. The stub subroutine is over here. First of all, we have to indicate the return line number, which is post, There's nothing after stub, or the invocation of stub. Then we have to allocate for all the local variables. We have two local variables here. We have first day and last day. How many columns should I allocate total for both local variables? 2 columns or 6 columns? We need 6 columns, okay? Because 1 column can only be used to represent a number, can only be used to store a number. A date consists of 3 numbers: the year, the month, and the day of month. So that's why the allocation of columns for our local variables gets a little bit more complicated. Because when we talk about first day, we are actually talking about a record. In other words, first day has several components. It has the component called year, it has the component called month, and it has a component called day of month. And because first day is a local variable, all of these start with unknown values. Okay? Are we doing okay so far? Now, this is a combination of the concepts that we already know, which basically means local variables are initialized. But we are adding on top of that concept how to deal with a record type. Because when you use a record type, then all the columns are become unspecified. And then we have another local variable, which in this case is last day. And it's the same thing. Last day is a date, which basically means it also has a year, a month, and a day of month. And all of these are also uninitialized. Just shrink the columns a little bit. Fit a little better. So are we doing okay so far with the 7 columns that we allocate in order to invoke stub? Any questions at this point? I know the post is not on the same row, but that's just cosmetics. No questions? Okay. If there are no questions, we'll execute line 9. All the way up to line 14. I'll just combine the execution of all 6 lines because that all that they do is to initialize each of these columns individually. So year of the first date is going to be 2011. Month is 1. Day of month is 18. And then for last day we have May 15th.
So you don't update those line by line?
Well, it's just just so that we can get through it quickly. So this will represent line 9 all the way up to line 14, the execution of those lines. 9 to 14. There we go. Okay. Are we doing okay so far? It's just a shorthand, so that I don't track down the lines that are not so important individually. Are we doing okay so far? Now, we get to line 15. Line 15 is not so easy. What do we do on line 15? Line 15 wants to print out the value that will be returned by is earlier than. So that means I cannot do the print yet. I have to first invoke is earlier than, and we have to use return info in this case. So in this case, we have to allocate a column to specify return info. And return info is going to say we have to get back onto line 15 because the printing part is not done yet by the time the subroutine has returned. That's the easy part. The next part, if you look at line 15, is how do we pass an entire record, first day, to X as a parameter and do the same thing with last day that is being passed to Y? Okay, what is passing by value again? Passing by value involves the use of a copier. You take the original thing, you make a photocopy, and then you give the subroutine a photocopy of the original. So it is the same thing here, except we are not making a photocopy of one integer, we're making a photocopy of the entire date. One date has 3 integers built in, but that's okay, we have a fairly big copier, so we can copy the entire thing and pass the copy along to the subroutine. Now, in terms of the trace, this is going to be kind of troublesome, so that I will just use copy and paste. Just being lazy here. Change the name of the first one to parameter x. Change the second one to parameter y. Oops, y. And we also have to make sure that we get rid of these question marks here. And let's see, can I delete shift cells up? Okay, there we go. Okay, let me fix up the width a little bit. And I'll zoom out just a little bit so that we can see what it looks like. Overall speaking. This is the trace up to this point. I have just passed first day, which is a local variable in stub, to parameter x, which is earlier than. And then I also passed last day, which is a local variable in stub, to parameter y by value, which is a parameter in is earlier than. So now we have this entire thing. This is our current context when we execute in is earlier than. Now you can also see how wasteful it is when you pass an entire record by value, because you are making a photocopy of the entire thing. We're making a photocopy of first day, and it becomes x. We make a photocopy of last day, it becomes y. So this is taking up a lot of columns. And that's why when you take your next class in cisp300, a lot of times you only pass by reference. When you have bigger objects to pass or bigger variables, you only pass by reference. Now when you pass by reference, there's always a danger of the subroutine changing the original item, because now the subroutine has a way to go back to the original item. In cisp300, they will talk about mechanisms that is a part of the language to make sure that the subroutine does not do that when it's not supposed to. But in this class, we'll just use pass by value in this case, just to illustrate that it can be done. It's just kind of wasteful to do it this way. So let's go ahead and continue to trace the program. I'll split the screen so that we can see just the part that we need to see, and that we can't even fit that part on the screen. We get into the subroutine of is earlier than, starting with line 21. So here's the execution of line 21. Line 21 is comparing the y, the year component, to the y, the year component between the two dates. I'm just using y to represent year so that I don't use up too much space. Is that true? Is the year of x less than the year of y?
False.
It's false. Very good. So if that is false, where do we go? We go to line 23, which is the second condition of the multi-branch conditional statement. Is x dot y equal to y dot y?
Yes.
Okay, that is true. So now we move on to line 24. Line 24 is just comparing the months. X dot m, which is month, is that the same as y dot m?
You're supposed to be checking less than.
It is true because y has a month of May and x has a month of January.
Line 24 evaluates whether x is less than y not equal. Yeah.
Line 24. Oh, okay. So less than symbol. Thank you. Okay. Never mind. That was me not reading the code correctly. Okay. So if line 24 is true, then we go to line 25. So here we are at line 25. Line 25 is going to return true. What do we do when we return true, or whenever we return a value? We copy and paste the return info cell. We change the question mark to the value that we are returning. In this case, it is just true. And we are done. We're done with the return statement itself on line 25. Okay, now this is the tricky part.
Do you have to deallocate the? Do you have to deallocate those lines up?
Yes,
there?
we do, but not at this point. because from line 25 we have to decide where to go next. Now remember, in this case, in this case it doesn't matter because I structure the code so that the return statement is the last thing that we do, regardless of whether regardless of the programming language. In this case, there's nothing else after the line of return on line 25, because this is the end of the then branch of this conditional statement. This conditional statement has nothing else, after the branch that is in, and that means we go all the way out to line 34 anyway. If you do this in C, in cisp300, you have no choice but to go to line 34 because that's the end of the subroutine and that's the definition of the return statement in the context of a C programming language. So here we are at line 34. Line 34 being the end of the subroutine. We'll first look up the return info cell and say, okay, we have to go back to line 15 to finish up the print statement. But after that, we also have to remember to clean up all the columns. In this case, the columns, there are 7 columns to clean up, and we can use either the old way or the new way to represent the columns are gone. And just I'll just kind of X them out like that. Now we are back to line 15. Line 15 now looks like this because we already know what value we are supposed to print. So we'll just say that we print the value of true, and then we go to post, and we're all done. Are there any questions about this subroutine or the trace? Let me just show you the trace, the entire trace, because it's long, but it does use the same concepts that we have talked about so far. It's just that when we pass an entire record by value, we have to make a copy of every single column of the original, which is kind of wasteful. Are there any questions about this trace? Yep.
The only problem is you didn't do line 16.
Line 16. Is there a line 16?
You're supposed to end define stuff.
Define stuff was earlier than.
Oh, okay. Sorry. My fault. Okay, let me fix that up. When we get back to line 15, we have to proceed to line 16. Okay, that's my fault. If I were to grade this one, I would have only gotten partial credit.
Yeah.
And you can tell right away because there are some columns that are allocated on the fly that were not deallocated. So very good. Good. So on line 16, we get to the end here. We look at the return line number. That reminds me to go back to post. And then after that, I will deallocate all of these columns. And then we get to post. Thank you. Very good. Any other questions? No other questions? Okay. So we'll continue to talk about records, probably through Thursday. And then starting next week, we'll move on to talk about more kind of interesting topics. We'll start with ADT, Abstract Data Types, which is a precursor to object-oriented programming. Okay, but it does serve the purpose of explaining why do we want to do object-oriented programming and why do we want to write programs in a particular way that makes everything easy to maintain. So that's kind of for the future. I'll let you guys go and see you guys on Thursday. Don't forget the homework that is due on Thursday.